Okay, welcome to JCE Connect. In the previous class, we were discussing about the relations with the temperature and the dissolved oxygen. We already discussed that how exactly the temperature is inversely proportional to dissolved oxygen, and how exactly it is going to affect the uh, the treatment process treatment process. So then we'll go with the color. So of course, um, the fresh wastewater, it is the light brownish gray. Uh, with time, it will turns to dark gray. And black means it is in septic conditions. So initially it will be in brownish color. Then as the time passes, it will reaches to the dark gray. Then ultimately it will be like a black or a septic conditions. Normally we can say it is a, when you observe any black color, then you can say it is the septic. Then dissolved oxygen, it will be zero. Means when you say it is a dissolved oxygen zero means the most of the fish will not survive. It will be, it's going to die. Sometimes it will turns to pink color. This is due to algae. And in some of the industrial process also, you will get some of the colors. Of course, that depends on the type of uh, processing. Depends on type of, that depends on type of processing. So then, of course, this color is measured in the Hazen's units. Hazen's limits. Then turbidity. Turbidity, of course, color and turbidity, it has its own difference. Now, the color normally it is due to the dissolved solids. And the turbidity, what we are speaking now, it is due to colloidal as well as suspended due to suspended solids. So when I say it is a dissolved solids, best example is if you take Pepsi. Pepsi, what you can do is that it is due to the dissolved solids. It is completely dissolved. Even if you filter that with the help of some of the filter papers, you won't get any things on the filter papers. But turbidity, if you filter it, some of the particles, it is going to settle on the filter paper. So, of course, this turbidity, it is the measure of light transmitting properties of water. It is a very, if I want to explain it, so assume that it consists of water, this level. So assume that it having some of the colloidal solids. So then, if I pass the light through this transparent glass, first whatever the light is there, it is going to hit all these particles. It is going to hit to the all these particles. When the light is going to hit all these particles, suddenly the light will reflect like this, or sometimes it will be come like this. So means some of the particle will it will transmit to the other direction, and some of the particles will come back. This is only going to happen in this turbidity, but in color it is not going to happen. Color, as I already said, that water will be there, Pepsi will be there, whatever the light, it will be the 100% it will. So then we can call it as 100% transmittance in color. But here you won't get. Wherever in the turbidity, even the principle of working of this turbidity is depends on the light transmission and absorption. Two principles are very important. First one is absorption and transmittance. Transmittance. So both are inversely proportional. So it is inversely proportional. So absorption and the transmittance are inversely proportional. So absorption in the sense, assume that this is a particle which is present in the water. So light is hitting to this particle. So means some of the particle it is absorbed by, some of the light is absorbed by this particle, and how much it is going to absorb, then remaining it will be transmitted back, means transmitted to the other side. Means if it is 100% absorbance, no transmittance. Means if it is 100% absorbing, then you won't get any light on the other side. Means that is a zero transmittance. Sometimes if no obstruction will be there, like your dissolved solids are there, so whatever it will be there, then in this path no particle will be there, then 100% you won't get. Means there is zero absorption by the particles, 100% it will be transmitted. So like that, so absorption and transmission both are very important whenever we are discussing the turbidity. Then the unit of turbidity is nephelometer. Nephelometric, turbidimetric unit. Metric unit. Normally we can call it as NTU, nephelometric turbidity unit. And normally we will measure in terms of turbidity meter or nephelometer. So one instrument is there that will use it to study this turbidity. So then dissolved oxygen is of course one very important component that we already, some part of this dissolved oxygen we already discussed. So the dissolved oxygen we will measure, it can be measures the amount of whatever the gaseous oxygen that is dissolved in aqueous solution. So then dissolved oxygen means whatever the oxygen which is dissolved in the water, that's it. It is one of the most important parameters in aquatic systems that I already discussed. If it is going below 4.5, then normally it is the fish life will not survive. This gas is an absolute requirement for the metabolism of aerobic organism, and also it influences on the inorganic chemical reactions. We'll see which are the organic things, organic reactions and inorganic chemical reactions. Therefore, knowledge of the solubility is very important. The knowledge of the solubility and dynamics of this oxygen distribution is essential in interpreting both biological as well as the chemical processes within the water bodies. So, whatever the distribution we are talking about, or the dynamics, if I say it is a dynamics, how exactly the O2 is penetrating how exactly this O2 is penetrating into the water body as the water moves. This is, we can call it as dynamics of the dissolved oxygen. Means normally this will always deals with the surface water. That is, for example, river is the best example. What will happen is that as the river water starts moving, how exactly the dissolved oxygen that is present in the atmosphere, it is going to accumulate in that river. How exactly it is going to now transfer by layer. So that we can call it as the dynamics. The solubility means the solubility, whatever you are talking about, it depends on the temperature that we already discussed. The solubility of the oxygen, um, that is uh, in the water, it depends on temperature. As the temperature is go on increasing, the solubility is going to decrease. So then oxygen gets into water by diffusion, of course, from surrounding air that I already discussed, by the aeration. So how exactly this aeration is going to happen? So assume that the river is flowing like this. What will happen is that as it move from this direction to this direction, or if it is moving in this direction, so whatever the layer of this, it will come in contact with the atmospheric oxygen. So when it comes in contact with the atmospheric oxygen, then automatically the dissolution is going to happen. That's what we can call it as diffusers. Best example for diffusion is your aquarium. In aquarium, you can see that the oxygen is supplied with the help of the one diffusers will be there in like this diffuser. One diffuser will be there, so it is having the holes. So with that, the oxygen is going to help of the diffusers. So if you want to increase the oxygen content in the aquarium, so then and as a waste product of photosynthesis. The amount of dissolved oxygen gas is highly dependent on the temperature that we already know. The atmospheric pressure also has an effect on the dissolved oxygen. So if you see the temperature profile as well as the pressure profile of the surrounding environment is totally different. If you say as the graph as the height means as we move towards from we have different layers will be there in the environment like troposphere, mesosphere. Like that, we have different layers will be there. When we are moving from the uh, troposphere to some of the next level, normally the temperature level it is go on decreasing. The temperature profile will be up like this normally up to mesosphere it will decrease again it will increase like that the same way the pressure also it has its own effect as you move towards the pressure will go on increasing as you move towards the top. So as the of course it depends on the whatever the pressure it is depends on the depth. Suppose if the depth of water go on increasing towards downwards, then normally whatever the pressure, it has its own influence. So then the amount of oxygen or the temperature that we already discussed, the warmer the water, lesser the oxygen. So here one very important that is the saturation point. The saturation point, if you ask me, saturation point. So normally the saturation at 0 degree centigrade that is maximum will get 14.1 milligram per liter. This is what the saturation point. Then at 25 degrees centigrade that is not the saturation but 25 9 literally 9.1 milligram per liter. So then the saturation point what we are discussing it's very important. As the temperature go on decreasing um, up to some point it will go at 0 degrees maximum it will reach 14.1 milligram per liter. Then even if it goes below 0 that is a maximum 14 point that is the saturation point of the dissolution of oxygen in the water. And at 25 degrees centigrade normally the oxygen will be 9.1 milligram per liter. Then the environmental significance of this dissolved oxygen we'll discuss in the next class.